Hello, here's some more questions on Newton's laws and various things associated with that. So we're starting with some definitions. We've got state the principle of conservation of linear momentum. So you want a couple of things here. You want to say that total linear momentum remains constant, but the other thing is that is in a closed system. So make a mention of closed system in there. Otherwise, you haven't really stated the full conservation law. Then we need to explain what is meant by inelastic collision. So inelastic collisions are where we get some kinetic energy loss in the collision. This is unlike the elastic collisions where we don't have a kinetic energy loss. So remember, in collisions, momentum is always conserved, but kinetic energy might not be. Sometimes we lose some of that kinetic energy to things like sound and heat and deformation of materials and things like that. So yes, so we need to make that distinction. Right, so that's dealt with those. Now we're on to some calculations. So we've got these blocks hitting each other. Is there anything in the text that's not in the picture? No, doesn't look like it. It's all there. So what do they want? They want us to calculate V, not surprisingly. So this is going to be our conservation of momentum, because we can always do conservation of momentum in collisions. We don't want to do conservation of energy, because we know it's inelastic and we've got no way of quantifying the energy losses out of kinetic energy, those transfers out of kinetic energy. So we have to do momentum as usual, vector quantity. So we need to keep positive. I'm going to go in the right direction. So 3 times 2.4 minus 2 times 1.2 is going to be equal to V times the total mass, which is 3.6. So what is that here? We've got 7.2 minus 2.4 divided by 3.6, and that is V. So what we got, 2 minus 2/3, so 1 1/3, let's say 1.3 meters per second. But it's 1 1/3 that we've got there. Then show that the collision is inelastic. Right, so now we're having to look at our energy and show that they're not the same as each other. So the energy before is going to be a half of 2.4, so 1.2 multiplied by 9 plus 0.6 multiplied by 4. And we need to show that that is not equal to half of the total mass, which is 1.8, times this was 1 1/3 squared. So we need to show these are different. So we're going to have 1.8 divided by 9 is 0.2 multiplied by 16. So we've got 16 over 5. Okay, so that is 16 over 5, 3.2, give or take. And we need to show that it's different on the other side. So we've got a 2.4 and we've got a 10.8, so what's that, 13.2, I think, if I've remembered that correctly. I think that's the right numbers, it looks about right. So yeah, these are clearly not different. We've lost about 10 joules of kinetic energy in the collision. So there we go. Right, on to the next bit. We've got a helicopter viewed from above with these 5-meter blades on there. The blades rotate in a circle at 5 meters. When the helicopter is hovering, they propel air vertically downwards at 12 meters per second. Assume the descending air occupies a uniform cylinder, 5 meters radius. And there's the density. Show that the mass of air propelled downwards in 5 seconds is about 6,000 kilograms. Right, so we need to get the volume of this cylinder, a 5-second cylinder, and then multiply it by the density. Right, so in 5 seconds, it's been propelled, the air has been propelled down 60 meters. We've got 60 meters worth of air there in this cylinder, because we got 5 meters, 12 meters per second, sorry, for 5 seconds. So the cylinder is going to be our pi r squared, so pi times 5 squared, 25 pi, multiplied by this 60 height. That's our volume. Multiply that by the density of 1.3. And, well, we're going to have to go to the calculator because of this pi. 6127, so 6100 kilograms to two significant figures. So that's come out okay. Now we need to calculate the momentum of this mass of descending air. So that's going to be the mass times the velocity. So 12 times that. Sorry, that's the mass. The velocity is 12. So 12 times our 6127 gives us 73523. So 74,000. So you can either put that kilograms meters per second or Newton seconds, whatever you want. So let's go Newton second. Force. What is the force provided by the rotating helicopter blades? So the force is the rate of change of momentum. This is our change of momentum. So we need to now divide that by the time. So divide that by 5. Well, let's go back to this 73,001. Divide that by 5, and we get 14705. So 1500 newtons. Sticking to the two significant figures. And then what is the mass of the hovering helicopter? Right, okay, so in this case we've got the helicopter, which is it's got the weight going down, it's got the force going upwards, which is our Newton's third law pair with the air that's being pushed down. So it's pushing the air down with 15,000 newtons. The R here is the equal and opposite, according to Newton's third law, pair to this 15,000 newtons. So that will also be 15,000 newtons. So the weight must be 15,000 newtons if the helicopter isn't moving. So our mass is going to be that divided by G, which is going to be, well, let's go back to the 14,705 divided by 9.81. So we get 1499. So 1,500 kilograms. So a nice chain of calculations there, connecting all of these things together. Right, moving on to what we got here. State Newton's second and third laws of motion. Right, okay, they want both of them. As always with these, the key is linking together forces with objects. So we want this connection between force and mass, really, in these. If we don't have an object, then, well, what's the force doing? It has to apply to something. So we can use that in our description. So for Newton's second law, we can say that the rate of change of momentum of an object, so linking this in with objects, is equal to the net force applied to that object. So yeah, we've got a nice then link to that object. Nice link between the two parts of the sentence then. Then similarly for third law as well. So for Newton's third law, we want to have the same thing. So we've got if object A exerts a force on object B, then object B exerts an equal force in the opposite direction on object A. So it's makes so much easier. As soon as you put object into it, then it makes it easier to write all these sentences out. If you're trying to describe these laws without referencing objects, you're going to get stuck. It ends up being a bit of a mess. Right, so that's dealt with those. Now we can look at this golfer using a golf club to hit a stationary golf ball. This is the force against time graph for that happening. So estimate the area underneath the graph. These are always difficult on screen. Let's count the big squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 17 and a bit, 18, 19, 20, 21. I'm going to say there's 21 squares. I mean, you'll be able to do this more accurately if you actually had a bit of paper in front of you. But we've got 21 squares, and each one of those squares is 500 newtons by 0.2 milliseconds. So we've got all of that. 500 times 0.2 is 100. So we can get rid of all of that and leave that as a 0.1. So we've got 2.1 all in all, Newton seconds. Name the physical quantity represented by this. Right, this is the impulse. Yeah, so yeah, not much more to say about that. That's what it is. It is the impulse. I mean, some people might say, oh yeah, well, it's the change in the momentum. Yeah, okay, but is a change in something a physical quantity? Probably best to go with impulse. I mean, it is change in momentum, but when they're asking for a particular physical quantity, as they've got here in the question, then go with impulse. Right, show that the speed of the golf ball, there's the mass, as it leaves the golf club is about 50 meters per second. So this impulse, this is our change in momentum, as we just said. So if we've got 2.1 divided by 0.046, that will give us the initial velocity. 2.1 divided by 0.046, so 46 meters per second. 46 meters per second, right? The ground is level. Ball leaves the ground at a velocity of 50 meters per second at an angle of 42 degrees to the horizontal. Determine the horizontal distance traveled by the ball. So we need the time of flight. Now the time of flight, the initial vertical component of the velocity is 50 sine of 42 degrees. So we need that to drop down to 0. So we need that change in velocity, which is going to be our acceleration multiplied by time, because change in velocity is the accumulation of the acceleration. So our time of flight is then going to be double this. So this is the time to reach the maximum point. It's going to be the same amount of time to drop back down again. So if we do 50 sine 42 divided by g, then we get 3.41. So time of flight is going to be double that, equals 2 times t, which is 6.82 seconds. Then all we got to do is multiply that by the horizontal component, which is 50 cos 42 degrees, and that will say how far it would have gone in the horizontal direction. Cos 42, which is 253 meters. 253 meters, so 250 meters to two significant figures. So then we got the usual state one assumption. So we just go with there's no air resistance. That's our standard go-to assumption when it comes to projectiles. All right, 2 to go. Particular collision between two objects is inelastic. Place a tick at the end of each statement that applies to such a collision. Right, so is the magnitude of the impulse on each object the same? Yes, it will be. That's to do with Newton's third law, as we saw earlier on in all of this. You've got the same collision time for each object because they're participating in the same collision, and they've got equal and opposite forces. So you've got equal and opposite impulses. Kinetic energy and momentum are conserved. No, I mean, that's the whole point of inelastic, is kinetic energy isn't conserved, momentum is. So we don't have that one. Total energy is conserved. Well, yes, total energy is, the kinetic energy isn't. So that's a tick. After the collision, the objects have the same momentum. No, I mean, we don't know. It depends on the nature of the collision and the setup of how everything has interacted. So we've got 2 ticks there for the first one and the third one. Right, now we've got a tennis ball hitting a wall. They've given us the speeds on there. The mass is 0.06 kilograms. They've given us that one. Oh, we've got a time of collision. So calculate the loss of kinetic energy. So the loss of kinetic energy is, well, we've got half mv squared for each one. What was the mass? 0.06. So we've got 0.03. That's our half m. And then we've got the v squared, so 144 minus 81. So not very big in all of this. So what's the difference? That's 63. So 3 over 100 times 63, 189 over 100. So 1.89 joules. We're still on two significant figures, so 1.9 joules. So that's that one. Calculate the magnitude of the average force exerted by the ball on the wall. Right, okay, so the average force multiplied by the time is going to be equal to the change in the momentum. They've given us the time, so our average force is, well, I mean, I suppose another way is just writing straight down Newton's second law. It's the same equation. So what's our change in momentum? It's gone from, remember, this is a vector quantity. So we've got a difference between, we've got 12 times 0.06, but it's changed to, so we've got to add on 9 times 0.06. And we need to divide that by the time, which was 0.15. Okay, so, well, we could, that's 15 over 100. So let's multiply by the 100 at the top, divide by the 15. So these are by 6. So we've got, what's that, 21 by 6. So 126 over 15 is our average force. So what's that going to be all in all? We've got, well, 6 15s are then 90. And then we've got 8 of them and 6 15ths left. So it's 8 and 2/5, 8.4 newtons. The magnitude of the average force exerted on the wall by the ball during this collision. Well, that's going to have to end up being the same, isn't it? Because if you've got the force on from Newton's third law, it's going to be the same. It's going to be equal but opposite direction, but the magnitude will be the same. So that's also going to be 8.4 newtons. Okay, last up, we've got a car of mass 970 kilograms travelling at 27 meters per second when the brakes are applied. Car is brought to rest in a distance of 40 meters. Calculate the kinetic energy of the car when it's travelling at 27 meters per second. Okay, a nice easy starter. So the kinetic energy is going to be a half times 970 times 27 squared, which is, yeah, let's go to the calculator on that. 353565. 353565. So we're still two significant figures. 3.5 times 10 to the 5 joules. Hence, calculate the average braking force on the car. State any assumption that you make. Right, so this is going to be, so the work done is energy transferred, which is the force, average force multiplied by the distance. So we need to divide this by 40. Divide by 40, because that's the stopping distance, which is 8,800, give or take, newtons. So the average force is 8,800 newtons. And we needed an assumption, so we'll say that there is no air resistance, because if there was air resistance you'd have a bit more force helping it to come to a rest, not just the braking force. Right, so that's dealt with part A. Part B, the car has 4 brake discs, each of mass 1.2 kilograms. The material from which the discs are made, specific heat capacity. Right, we haven't actually done this yet in detail, but it's pretty straightforward to do, especially as they've given us all the units here. Calculate the temperature rise of each disc after braking from that speed. Assume all the kinetic energy of the car is converted into internal energy of the brake discs equally during braking. Right, so we're saying that each disc gets, what was our, so 353565 divided by 4 joules. 353565 divided by 4, so that's the amount of energy that's gone into it. And the specific heat capacity is 520 joules per kilogram per Kelvin. Right, so it's a 1.2 kilogram disc. So for each 1.2 kilograms, we're going to need more joules. We're going to need 520 multiplied by 120, and that'll be the joules per Kelvin. And then we've got our number of joules there. So what we're doing, this is our 88391, and we need to divide that by 520 times 1.2. So I suppose another way of putting that, if you're doing a unit analysis, you put the specific heat capacity on one side, joules, kilograms, Kelvin. On the other side, we just need to match these things up. So we've got the 88391, which is in joules. So we need to divide by the kilograms and the temperature difference. So you put all of those together and everything comes out all right. So you just rearrange that to make delta T the subject. So it's now the 88391 divided by 520 divided by 1.2 gives us 142. So delta T is 142, which is 140 degrees Kelvin or centigrade, whatever way you want it, to two significant figures. Oh dear. Right. State and explain 2 reasons why the actual temperature rise will be different. Right, well, there's loads of things you could do for this. So let's say there'll be some of the, well, we've got the air resistance thing, so that's one of them that we can put in. So air resistance will reduce the breaking force. So some of the energy will go into the air. So some kinetic energy into the air. So that's one thing we've got. You could have the brake discs will cool a little during the braking time. So that's another one, because you've got airflow around them and they're hotter than the surroundings. So that's another one we've got there. You might get, think of other things that happen when you're braking. We might get wheel locking. If you've got wheel locking, then you're going to get heat going into the tyres, because the tyres are going to suddenly be rubbing along the ground with extra friction. So you've got that as well. So that's going to be kinetic energy into tyres. So that's 3 things off of that. Then suggest 1 modification to the design of the disc braking system that could reduce the temperature rise of the discs. Right, well, we can look at the formula then. I mean, if we've got this calculation that we've done here, well, we can't change the bit at the top. We can't change that energy, this kinetic energy that needs to be dissipated. That is still unchanged, but we can change these 2 things. So that gives you 2 options then for the modification that you might want to make. You can change the specific heat capacity. So if you increase the specific heat capacity, you're going to get a reduced temperature rise, or we could change the mass of each disc. So if you increase the mass, so go for one of those, increase the specific heat capacity or increase the mass. That's the nice thing about writing out the formula on it as well, that you can go back and say, well, what did I do in my calculation? And how could I change the numbers? What do I have control of? If you were an engineer, you go back and look at the things that you have control of. Things you have control of are the material, which gives you the heat capacity, and the mass. Okay, admittedly, they're going to have other knock-on effects. You don't want to make the brake disc too heavy, otherwise you're carrying around these massive, great big brake discs on each wheel. But you've got a bit of leeway there. And if your only objective is to reduce the temperature rise, then go for it. So yeah, 2 options for the last part.